30 years ago, a satellite looked down at the Atlantic Ocean and recorded something unusual. Nobody noticed. The next year, it recorded it again. And the year after that. For 3 decades, the data just sat there, archived, time-stamped, and ignored. While the ocean was quietly sending us a warning we didn't have the framework to read. Here is what it was saying. The engine that keeps Northern Europe from being a frozen wasteland is failing. Not someday. Now. There are 2 stages to what scientists are now calling a potential collapse of the Atlantic's most important ocean current. Stage 1 is slow, gradual, quiet, easy to miss. Stage 2 takes approximately 2 years, and by the time it begins, it is already too late to stop it. Scientists just built the first instrument capable of reading exactly how far along that failure actually is. And they pointed it at 30 years of satellite data we already had sitting in our archives. Stay with me, because the stage it's pointing to is not the one you're hoping for. Britain sits at the same latitude as Siberia. Let that settle for a moment. London lines up on the map with parts of Russia where temperatures regularly plunge to -30 in January, and the ground stays frozen for months on end. Norway sits parallel to the southern tip of Greenland. And yet somehow, Northern Europe has mild winters, functioning agriculture, and cities that don't require survival gear to walk through in February. That is not a coincidence. That is not geography being generous. That is the result of an invisible machine, a planetary circulatory system running through the Atlantic Ocean that has been quietly pumping tropical heat northward for thousands of years without a single day off. And right now, for the first time in the history of climate science, researchers at Utrecht University have built something that nobody had before. A fuel gauge for that machine. Not a speedometer telling us how fast it's running. A fuel gauge telling us how close it is to empty. And when they pointed that gauge at 30 years of satellite data we had already been collecting without fully understanding, the reading came back with something that should have been headline news around the world. We are already inside stage 1 of a pre-collapse warning sequence. The Gulf Stream has drifted approximately 53 kilometers northward since 1993. That matches, almost exactly, what the model predicted would happen in the early phase of a failure cascade. The data was sitting in our archives the entire time. We just didn't know what we were looking at. We do now. Satellites have been mapping the surface height of the ocean continuously since 1993. That is not a trivial detail. Ocean surface height is not random. It reflects the speed and position of the currents moving underneath. The way a river's surface bulges slightly where the water runs fastest. For 30 years, those satellites have been sending back a picture of exactly where the Gulf Stream sits. And for 30 years, that data has been archived, processed, and largely set aside without anyone connecting it to a potential collapse sequence. Subsurface temperature records go back even further, to the 1960s, and they independently confirm the same thing the satellites show. The current has been drifting northward. The frustrating part, and this is the part that should make you sit up, is that the signal was not hidden. It was not classified. It was not buried in some obscure journal nobody reads. It was recorded, time-stamped, and available to anyone who looked. The reason nobody raised the alarm is not that the data was missing. It's that science didn't yet have a theory that told anyone what northward drift actually meant. You can measure a fever for decades without knowing it's a symptom of something serious if you've never seen the disease before. The Rapid Array, installed in 2004, confirmed that the Atlantic Meridional Overturning Circulation, AMOC as scientists call it, was slowing down. That much was known. What was not known, until now, was how close that slowdown placed us to an irreversible threshold. The real breakthrough at Utrecht was not discovering new data. It was learning, finally, how to read the data we already had. And what it says is not reassuring. The reason climate models kept missing this comes down to resolution. For decades, the standard grid size for ocean modeling was roughly 100 kilometers per cell. That sounds precise until you realize that the Gulf Stream is a tight, narrow boundary current, one of the most tightly structured flows in the entire ocean. And at 100-kilometer resolution, it essentially gets smeared into the surrounding water. You can't see the thing you're trying to study because your lens is too blurry. The Utrecht team, led by René van Westen and Henk Dijkstra, changed that. They ran their simulation at 10 kilometers per cell, 10 times the resolution. That doesn't sound like much until you grasp the computational cost. The Snellius supercomputer running at full capacity took the equivalent of what would have been millions of years of calculation on standard hardware. The simulation they ran introduced freshwater forcing gradually, mimicking the slow melt of Greenland ice pouring into the North Atlantic. And at that resolution, something emerged that previous models had been completely blind to. Two distinct and separate stages of collapse. Not a gradual fade. Not a smooth slowdown. Two stages separated by a period of relative quiet that could easily be mistaken for stability, followed by a second stage where the entire system unravels in roughly 2 years. For the first time, the model predicted something specific and observable, a northward drift in Gulf Stream position during Stage 1. And when they compared that prediction to the 30 years of satellite altimetry data already sitting in the archive, the match was confirmed. This is not just theory anymore. This is theory meeting reality, and reality agreeing. Stage 1 is what we appear to be in right now. It is the slow phase. The current weakens gradually over what the model estimates as roughly 400 years, and during that time, the Gulf Stream drifts northward at a pace that is almost imperceptible year to year. It feels like stability. It looks like normal variation. The climate shifts, but not dramatically enough to trigger alarms in the way people imagine. It is, in the language of physics, a system moving slowly toward a threshold, like a chair being tilted backward, degree by degree, while someone sits in it. You can tilt a long way before anything dramatic happens. And then there is Stage 2. Stage 2 is not gradual. Stage 2 is the chair falling. When the deep circulation, the cold, dense, salty water that sinks near the Nordic seas and flows southward along the ocean floor, weakens past a critical point. It loses the ability to anchor the Gulf Stream in its current position. The mechanism is almost mechanical. The deep current acts like a pin holding the surface current in place. When that pin fails, the surface current doesn't slow down gracefully. It slips north, loses its organizing structure, and the entire overturning circulation collapses within approximately 2 years. 2 years. The system doesn't announce itself at the end. It doesn't give you a loud warning right before the threshold. The loudest signal comes earlier, in the drift. In the slow northward migration we've already been recording. After that, the collapse happens faster than any meaningful political response could possibly be organized. The most dangerous part of this story is not what happens at the end. It's how quiet everything seems right before it. Here is where the numbers become genuinely uncomfortable. The model's Stage 1 runs for approximately 400 years before the collapse sequence begins in earnest, with full circulatory failure arriving roughly 25 years after the end of Stage 1. The Gulf Stream has drifted approximately 53 kilometers northward since 1993, according to satellite data. The model predicts a total northward drift of approximately 133 kilometers across the entirety of Stage 1. If you do the rough math, and this is rough, intentionally rough, that places us somewhere around 40% of the way through Stage 1. That extrapolation, combined with the model's internal timeline, points toward potential collapse somewhere in the range of the late 21st century. somewhere around 2070 to 2095, if current forcing rates hold. But here's the trap embedded in that estimate. The word if is doing an enormous amount of work in that sentence. The model was run under controlled, gradually increasing freshwater input. The real world is not controlled. Greenland is melting faster than the linear trend would suggest. Atmospheric feedbacks are not fully captured. Wind patterns are shifting. Every one of those variables has the potential to compress the timeline. The uncertainty in this estimate does not spread symmetrically into the future. It leans toward sooner. The clock exists. We just can't read exactly what time it says. And the next question, the one that actually defines what's at stake, is what exactly this system does for the planet that nothing else can do. Because that answer is where this story gets genuinely terrifying. The Atlantic Meridional overturning circulation is, at its most basic, a conveyor belt for heat. Warm, relatively shallow water flows northward from the tropics, releasing enormous quantities of energy into the atmosphere along the way, then cools, becomes denser, sinks to the ocean floor, and flows southward again in a loop that takes centuries to complete. The numbers involved are almost incomprehensible. A MOOC transfers roughly 1 petawatt of energy as it moves, that is 1 quadrillion watts. To put that in terms that mean something, that is approximately 50 times the total energy consumption of every human being on Earth combined. Every single second, being transported through a river of water you cannot see from the surface. This system has been running continuously for thousands of years. It predates every human civilization. It was humming along when Rome was built, when the first cities rose in Mesopotamia, when humans first crossed into the Americas. The entire arc of recorded human history, agriculture, language, architecture, science, all of it, has unfolded inside the stable climatic window that AMOC helped create. We did not build civilization despite the climate. We built it because of the climate. And at the center of that climate is a system most people have never heard of, cannot see, and have never been asked to think about. Remove it, and the climate does not simply adjust by a few degrees. It reorganizes. The atmospheric circulation shifts. Storm tracks move. Rain belts migrate. The change is not incremental. It is structural, and there is no backup system. The contrast becomes starkest when you actually look at a globe rather than a flat map. London sits at approximately 51 degrees north. So does Kiev. So does parts of Kazakhstan. Calgary, in Canada, sits at 51 degrees north as well, and Calgary gets brutal winters. Regularly -20, heavy snowfall, months of frozen ground. The difference between Calgary and London is not altitude, not local geography, not some quirk of urban development. The difference is the Atlantic Ocean and the current moving through it. The Gulf Stream carries water northward that began its journey near the Gulf of Mexico at temperatures around 27 degrees Celsius. As it moves north, it releases that stored heat into the atmosphere above Western Europe, like a radiator running through the wall of a house. The maritime climate of Northwest Europe, the mild winters, the relatively moderate summers, the lack of the extreme continental swings you see at the same latitudes in Russia or Canada, is not the natural state of that latitude. It is an anomaly. It is the product of a heat subsidy being paid continuously by the ocean. Without AMOC, climate modelers project average winter temperatures in parts of Northwest Europe dropping by as much as 10 degrees Celsius or more over the course of decades. Norway's coast, currently ice-free year-round due to that Atlantic heat, would begin to look considerably more like its latitude actually suggests it should. The anomaly that has made Northern Europe livable and agriculturally productive for millennia is not a permanent feature of the planet. It is a loan from the ocean, and there are signs the loan is being called in. Most people, when they think about ocean currents, picture the surface, the familiar arrows on maps showing the Gulf Stream curving northeast across the Atlantic. What almost nobody thinks about is what happens underneath. The surface current does not exist in isolation. It is anchored, stabilized, and in a very real physical sense, controlled by what happens in the water column below it. The deep western boundary current, the southward flowing return leg of the AMOC conveyor, runs along the western edge of the Atlantic Basin at depths of 2 to 3 kilometers. It is not a gentle trickle. It carries an enormous volume of dense, cold water, and its flow creates rotational dynamics that effectively pin the Gulf Stream to its current position in the ocean. Think of it this way: the surface current and the deep current are not independent systems running in parallel. They are coupled. They are part of the same loop, and the stability of each depends on the other. When the deep flow weakens, which is exactly what is happening as fresh water from Greenland dilutes the North Atlantic and reduces the formation of the dense, sinking water that feeds it, the surface current loses its anchor. It doesn't stop immediately. It starts to drift. It migrates northward, away from its historical position, in precisely the pattern the Utrecht model predicted. The instability begins below the surface, invisible to anyone watching the waves. It propagates upward, slowly, imperceptibly, over decades, until the pin finally fails, and the surface current slips free of its position entirely. That is the mechanism. That is what the data is showing, and the question of what actually disrupts the deep current's formation brings us to a process that has been accelerating quietly for decades. The full AMOC loop, when you trace it from beginning to end, is one of the more extraordinary things the planet does. It begins near the Gulf of Mexico, where the sun has been warming surface water to roughly 27 degrees Celsius. That warm, relatively shallow water moves northward along the eastern coast of North America as the Gulf Stream, fast, energetic, carrying an enormous volume of water and heat. As it pushes further north toward Iceland and the Nordic seas, two things happen simultaneously. The water cools, losing heat to the atmosphere above and helping warm the air over Western Europe in the process. And it evaporates, shedding fresh water into the atmosphere and becoming saltier and therefore denser as it travels. By the time this water reaches the Nordic seas and the area near Greenland, it has become cold enough and dense enough to do something remarkable. It sinks. Not gradually. It convects downward, plunging to the ocean floor in columns that oceanographers call chimneys, and in doing so, it drives the entire return flow of the conveyor. From there, the dense water flows southward at depth along the ocean floor, traveling the length of the Atlantic over centuries, eventually reaching the Southern Ocean near Antarctica, where it upwells and makes its way back toward the surface before beginning the circuit again. The entire loop takes roughly 1,000 years to complete. It is ancient, enormous, and astonishingly stable. Or rather, it has been astonishingly stable. Its stability depends on a very specific set of conditions at those Nordic sinking sites. Conditions that are, right now, being systematically altered. Here is the thing that separates AMOC from almost every other large-scale Earth system. There is no redundancy. There is no backup. There is no alternative circulation waiting in the wings that could step in and perform the same function if this one fails. The energy transfer AMOC provides, that 1 petawatt of continuous heat redistribution, cannot be replicated by any other ocean process operating at any realistic timescale. And it absolutely cannot be replicated by technology. The sheer scale of the energy involved places it beyond any conceivable engineering intervention. This is not a leaking pipe you can patch. This is not a failing power grid you can reroute. This is planetary infrastructure operating at a scale that dwarfs every human system ever built, and if it fails completely, irreversibly, and on timescales that make human adaptation the only available response. Not correction, not reversal, not repair. On a timescale relevant to human civilization, An AMOC collapse is permanent. The geological record shows that once this system has entered a collapsed state, it can persist for centuries to millennia before recovering. The civilization that experienced the collapse would not live to see the recovery. That is what makes this different from almost every other environmental challenge being discussed today. Most problems, even severe ones, have some degree of reversibility. This one, once it crosses the threshold, does not, which makes what is currently feeding the system's destabilization not merely an environmental footnote, but the most consequential geophysical process currently underway on this planet. And to understand what is driving it, you have to start with something as simple as the difference between saltwater and fresh. The physics here is remarkably simple, which is part of why it's so unnerving. Cold water is denser than warm water. That much most people know. But salinity matters just as much. Salty water is denser than fresh water. And density is everything when it comes to the deep sinking that drives the AMOC engine. The entire system depends on water arriving at the Nordic sinking sites with enough density to actually plunge to the ocean floor. If that water arrives diluted by fresh water, less salty, less dense, less inclined to sink, the convection chimneys weaken. The deep flow diminishes. The anchor on the surface current loosens, and the entire conveyor begins to slow. Greenland is currently releasing enormous quantities of fresh water into the North Atlantic through melt. Not theoretical future melt. Present tense, currently occurring, measurable melt. The ice sheet covering Greenland contains enough water, if fully melted, to raise global sea levels by approximately 7 meters. It is not melting all at once, but it is melting faster than at any point in the modern instrumental record, and the fresh water is flowing directly into the ocean in exactly the location where AMOC needs high salinity, high-density water to sink. The mechanism connecting Greenland melt to AMOC disruption is not speculative. It is one of the most well-understood processes in oceanography. The trigger is not something that might happen. It is happening. The only question that remains open is how fast the input is accelerating. And on that question, the news is not good. The dangerous assumption embedded in most public discussion of Greenland melt is that it proceeds in a straight line, a steady, predictable increase year over year that gives us decades to respond and adjust. That assumption is wrong, and the reasons it's wrong compound on each other in ways that matter enormously for the AMOC timeline. The first feedback is albedo. Ice is white and reflective. When ice melts, it exposes darker ocean water or bare rock, which absorbs more solar radiation, which warms the surrounding area, which melts more ice. The more Greenland loses, the faster it loses the rest. The second feedback operates from below. Warm Atlantic water is increasingly flowing beneath Greenland's outlet glaciers, the rivers of ice that drain the interior and deposit icebergs into the sea. That warm water undercuts the glaciers from underneath, destabilizing their foundations and accelerating the rate at which they calve into the ocean. The third feedback involves the ice sheet's own mass. Large glaciers move more slowly because their sheer weight presses down and creates friction. As they thin, that friction decreases, meltwater lubricates the base, and the ice begins to slide faster toward the sea. Each of these feedbacks is active right now. Each of them feeds the others, and none of them appears in models that assume linear melt rates. The Earth has encountered conditions something like this before, and when it has, the results have been both instructive and deeply sobering. Approximately 12,900 years ago, the Earth was warming. The last ice age was retreating. Glaciers were pulling back, and the planet was transitioning toward the relatively stable, temperate conditions that allowed human civilization to develop. And then, abruptly, temperatures across the northern hemisphere plummeted back toward near glacial conditions. Not over centuries, over decades, possibly faster. This event is called the Younger Dryas, and it lasted for approximately 1,000 years before ending almost as abruptly as it began. The leading hypothesis for what caused it involves a massive pulse of fresh water entering the North Atlantic, the same mechanism we're discussing now. As the Laurentide ice sheet covering North America began to collapse, it appears to have released enormous volumes of meltwater into the ocean, disrupting the salinity and density of the North Atlantic, weakening or shutting down the precursor of AMOC, and triggering a rapid reorganization of Northern Hemisphere climate. The same basic physics, the same system, the same mechanism. And it happened fast enough that a human lifetime would have spanned a significant fraction of the entire transition. The Younger Dryas is not a remote curiosity from the geological past. It is a proof of concept. It demonstrates, in the real record of the Earth, that this system can switch states, that it can do so rapidly, and that when it does, the consequences are civilizational in scale. We are not speculating about a process without precedent. We are observing a process with extensive, well-documented precedent and watching it replay in slow motion. The freshwater event most often linked to the Younger Dryas involved what geologists call Lake Agassiz, one of the largest lakes ever to exist on Earth. At its maximum extent, it covered an area larger than all of the modern Great Lakes combined, pooled behind the retreating ice sheets of North America. It was not a permanent feature of the landscape. It was a temporary reservoir held in place by ice dams and glacial topography, accumulating an extraordinary volume of fresh water over thousands of years. When those dams failed, whether through gradual melting or some threshold collapse, the lake drained catastrophically into either the North Atlantic or the Arctic Ocean, depending on the drainage route. The freshwater pulse was enormous. It was rapid. And the hypothesis is that it was sufficient to overwhelm the salinity of the North Atlantic sinking sites, suppressing the density-driven convection that drives AMOC, and triggering the Younger Dryas cooling. The parallel to Greenland is not exact. Greenland's melt is slower, more distributed, not a single catastrophic drainage event. But the physics is the same. Freshwater entering the North Atlantic at or near the sinking sites reduces the density of surface water, suppresses convection, weakens the deep flow, and destabilizes the overturning. The scale is different. The time scale is different. The mechanism is identical. And the mechanism has already proven itself capable of shutting the system down. The question we are now living inside is whether a slower version of the same process, running over decades rather than years, produces the same ultimate outcome. The geological record, frustratingly, suggests it might. The most important thing the paleoclimate record establishes is not the specific details of any single event. It is the existence of what physicists call bistability. The Atlantic overturning circulation does not exist in a single, unique, stable state. It exists in two stable states. One with strong overturning circulation, like the one that has supported civilization for millennia, and one with weak or absent overturning circulation, like what occurred during the Younger Dryas. Between those two states is a threshold, a tipping point, that once crossed does not allow for easy reversal. The system will settle into the new state and remain there, because each state is self-reinforcing once established. This is not a model artifact. This is not a theoretical curiosity. It is observed in proxy records from ice cores, deep sea sediments, and coral archives spanning hundreds of thousands of years. The Earth's climate system knows how to run without a strong AMOC. It has done it before, and it does not require catastrophic, sudden forcing to get there. It requires sustained pressure in the right direction, applied to the right part of the system, over sufficient time. The problem we now face is that we have been applying exactly that pressure for decades, to exactly the right part of the system, without recognizing what we were doing. The warning signs, meanwhile, have been showing up not as headlines, but as anomalies in weather patterns that most people have written off as just the new normal. Though, whether those anomalies are connected to what is happening in the Atlantic is itself a question that opens up an entirely different and deeply unsettling line of inquiry. The jet stream is, at its simplest, a river of fast-moving air in the upper atmosphere that circles the northern hemisphere and serves as the primary organizing structure for weather patterns across Europe and North America. It flows west to east, driven by the temperature contrast between the cold polar air to the north and the warmer mid-latitude air to the south. When that temperature contrast is large and sharp, the jet stream flows in a relatively straight, fast band. When the contrast weakens, when the poles are warming faster than the mid-latitudes, which is exactly what is currently being observed, the jet stream becomes slower and more wavy. The technical term is Rossby wave amplification, and the practical consequence is weather systems that don't move the way they used to. A storm that would historically track across the Atlantic in a week and move on might instead stall over the same region for 2 or 3 weeks. A blocking high-pressure system that might have lasted a few days might persist for a month. The direct link between AMOC weakening and jet stream destabilization is an active area of research, not yet confirmed to the degree of scientific consensus. But the mechanisms being proposed are physically coherent. AMOC transports heat that plays a role in maintaining North Atlantic sea surface temperature patterns, and those patterns influence the atmosphere above them. What is not disputed is that the jet stream has been exhibiting increased waviness over recent decades. Whether AMOC is the cause, a contributing factor, or simply weakening in parallel, is something the next decade of observation will likely begin to resolve. Europe has been experiencing something that meteorologists have taken to calling weather pattern persistence. The same basic atmospheric configuration repeating or stalling over the same regions for extended periods, producing what you might think of as stacked events. A wet autumn followed by an unusually wet winter, followed by a spring with repeated storm systems tracking along identical routes. Or, conversely, a blocking pattern locking a high-pressure system over Scandinavia for weeks at a time, producing drought in one region and flooding in another simultaneously. The concept of stacking refers to the way these persistent patterns allow impacts to accumulate. A single severe storm is a crisis for a week. The same intensity of rainfall distributed across 6 separate storm systems, all tracking the same route across the same watershed over 2 months, produces something qualitatively different. Saturated ground that can no longer absorb water. Overstressed infrastructure. Agricultural damage that compounds season over season. The link to AMOC and ocean-atmosphere coupling is suggested by the physical logic. The North Atlantic sea surface temperatures that AMOC helps regulate directly influence the atmospheric pressure patterns above. But the attribution science here is honest about its limitations. Correlation between observed pattern changes and AMOC weakening exists. Confirmed causation does not yet. What does exist is a coherent mechanism and a growing body of modeling work suggesting the relationship is real. The cleaner experiments the climate is now running on itself, unfortunately, are only going to produce more data the harder way. One of the more counterintuitive aspects of a weakening AMOS is that it does not produce uniform cooling. It produces redistribution. The system currently takes heat from the tropics and delivers it to northern Europe. When it weakens, that delivery stops, and the heat that would have been transported northward instead accumulates in the subtropical Atlantic. The result is a pattern where Europe gets colder, while parts of the tropical Atlantic get warmer, sometimes significantly warmer. This creates a world where global average temperature may continue to rise, while specific regions experience sharp local cooling, and where the weather extremes in any given location become harder to connect to a single simple narrative of more warming. The United Kingdom, for example, could simultaneously be experiencing warmer than average summers due to global warming, while facing increasingly severe and prolonged cold winters due to a weakening Gulf Stream, and the two signals would partially cancel each other out in the annual average, making the change harder to detect in the numbers without careful decomposition. This is part of why the early stages of AMOC weakening are genuinely difficult to see in everyday experience. The signal does not announce itself as a single, clean trend. It shows up as instability, as contradiction, as seasons that feel wrong in ways that are difficult to articulate but easy to observe. Record heat in one country, record cold in the next, separated by a few hundred kilometers in the same week. The climate does not become simply colder when AMOC weakens. It becomes more chaotic, and that chaos has a structure that we are only now beginning to read. Sitting above the Arctic is a large circulation of cold air that meteorologists call the polar vortex. Under normal conditions, it stays organized and contained near the pole, kept in place by the same temperature gradients that keep the jet stream stable. When it remains intact, it effectively seals the coldest Arctic air away from the mid-latitudes. When it breaks down, when something disrupts its coherence and causes it to split or wobble, fragments of that Arctic air can descend southward with remarkable speed, reaching as far as Texas or the Mediterranean, and producing the kind of cold snaps that make headlines for the sheer contrast they create with recent conditions. Polar vortex breakdown events have been increasing in frequency and severity over recent decades. The mechanism most often invoked to explain this involves the same reduced temperature gradients between the pole and the mid-latitudes that are proposed to destabilize the jet stream. And those reduced gradients are themselves a product of accelerated Arctic warming, which is, in part, a consequence of reduced heat transport from the south. The feedback pathway is long, and the individual links remain contested, but the system-level logic points in a consistent direction. A weakening AMOS reduces northward heat transport, changes North Atlantic sea surface temperatures, alters the pressure patterns that regulate both the jet stream and the polar vortex, and increases the frequency of extreme cold outbreaks at lower latitudes, even as the global average temperature continues to climb. Cold snaps in an era of global warming are not a contradiction. They may be among the first legible symptoms of a disrupting circulatory system trying to equilibrate. The honest scientific difficulty in all of this is that the climate system produces natural variability on a scale that can, and regularly does, mask trends that are real, but slow-moving. A single anomalous winter tells you very little. A decade of anomalous winters begins to mean something. 2 decades of consistent anomalies in the same direction, in the same systems, consistent with the same physical mechanisms, starts to constitute evidence. The challenge is that the political and social response to climate risk is not calibrated to the timescale on which the science accumulates. By the time there is enough signal to definitively overwhelm the noise, enough to satisfy every skeptic with a methodological objection, the system being studied may have already moved past the point where the signal's origin becomes irrelevant because the consequences are already in motion. This is a known problem in complex system science. The signal that truly matters, the one indicating a threshold approach, tends to be quiet relative to the background noise, precisely because of how tipping point dynamics work. The system appears stable until it doesn't. The early warnings are subtle, ambiguous, and easy to attribute to natural variability. And the moment the signal becomes unmistakable is roughly the moment it becomes too late to intervene. The same challenge applies to what a full AMOC collapse would actually look like in practice, which is a question worth asking very specifically, because the answer involves consequences at a scale and severity that the language of climate policy has largely failed to communicate. The most widely cited projection for a full AMOC collapse is an average winter temperature drop of approximately 10 degrees Celsius across Northwest Europe, occurring over a period of decades rather than centuries once the threshold is crossed. 10 degrees is not a small number. 10 degrees is the difference between a temperate maritime climate and conditions more closely resembling the interior of Scandinavia or the northern coasts of Canada. It is the difference between crops that grow and crops that don't, between winters that are uncomfortable and winters that are genuinely dangerous for infrastructure, agriculture, and the tens of millions of people who have built their lives and economies around a climate that no longer exists. London, currently one of the more temperate major cities in the Northern Hemisphere by latitude, would face winters more closely resembling those of modern-day Helsinki or Reykjavik. Sea ice could advance southward into the Norwegian Sea and beyond. Ports that are currently ice-free year-round, including ports critical to European energy supply and trade, would face potential icing for portions of the year. The agricultural zone of Northern Europe, currently one of the most productive farming regions on Earth, would contract sharply toward the south and the west. The physical infrastructure of these countries, the insulation standards, the road designs, the water system architectures, was built for the climate that AMOC provides, not the climate that exists at those latitudes without it. The adaptation cost alone would be staggering, and adaptation cost assumes sufficient warning time and political will, neither of which is guaranteed. The agricultural implications of a 10-degree average winter temperature drop in Northwest Europe deserve to be treated as a separate catastrophe rather than a footnote to a climate story, because the food system impact would not be limited to the directly affected region. Growing seasons in the United Kingdom, France, Germany, Scandinavia, and the Baltic states would shorten by weeks to months. Crops that currently define those agricultural systems, wheat, barley, rapeseed, sugar beet, a significant fraction of Europe's vegetable production, require minimum temperature thresholds that simply would not be met in many of the regions currently growing them. The knock-on effect on livestock is equally severe. Shorter growing seasons mean less fodder, more expensive winter feeding, and the same infrastructure challenges facing the human population. Europe is not merely a food producer for itself. It is a significant exporter, and any dramatic reduction in European agricultural output would immediately feed into global commodity markets, affecting food prices and availability well beyond the continent's borders. The historical precedent from smaller, shorter AMOC disruptions during past centuries, the Little Ice Age, for example, which involved only partial and temporary weakening, includes documented accounts of famine, crop failure, and population displacement across Northern Europe. Those disruptions were modest compared to what a full collapse would produce. The agricultural system is not a side effect of this story. For the majority of the world's population, it is the story. AMOC does not only regulate the climate of Northern Europe, because it is part of a global system of heat redistribution, its collapse would reorganize atmospheric circulation patterns across the entire planet. And one of the most consequential reorganizations would be the displacement of the tropical rain belts that govern monsoon systems in Africa and South Asia. The intertropical convergence zone, the band of intense rainfall that follows the sun's heating of the tropics, does not sit in a fixed position. It migrates north and south seasonally, and its average position is influenced by the temperature contrast between the northern and southern hemispheres. When AMOC weakens, the northern hemisphere loses heat relative to the southern, and that imbalance pushes the entire tropical rain belt southward. The West African monsoon, which provides the rainfall on which hundreds of millions of people across the Sahel and sub-Saharan Africa depend for agriculture and drinking water, would shift significantly. The South Asian monsoon that waters the Indian subcontinent, home to over 1.5 billion people, would be disrupted. The Amazon, already under stress, would receive altered precipitation patterns. The human population living under these rain systems did not cause the AMOC disruption and will not be the beneficiary of any policy response focused on European energy systems. They will absorb consequences on a scale that makes Europe's regional cooling look like a local problem. Over 1 billion people's access to water and food is entangled with rain belts that AMOC helps position. That is not a statistic. That is a civilization. Below the headlines about temperature and agriculture, there is a quieter catastrophe embedded in an AMOC collapse that would unfold in the ocean itself. The conveyor's overturning function is not merely about temperature. It is about the vertical movement of nutrients. Cold, deep ocean water is nutrient-rich. It carries the mineralized remains of organic matter that has sunk over centuries, and when that water upwells toward the surface, it fertilizes the sunlit zone where photosynthesis occurs. This is the mechanism that makes certain ocean regions extraordinarily productive fisheries. The North Atlantic is one of them. A collapse of the overturning circulation would dramatically reduce the upwelling of nutrient-rich deep water, starving the surface layer of the compounds that phytoplankton need to grow. Phytoplankton are not merely the base of the ocean food chain. They produce approximately half of the oxygen in Earth's atmosphere. Their decline would cascade upward through every level of marine life: zooplankton, small fish, large fish, marine mammals, in ways that would unfold over years and decades, progressively dismantling fisheries that currently feed hundreds of millions of people and represent critical economic infrastructure for entire nations. Iceland, Norway, the United Kingdom, West Africa, and many others depend on North Atlantic and adjacent fisheries to a degree that makes their disruption equivalent to a prolonged, unending agricultural crisis running in parallel with the temperature-driven one on land. The ocean food web collapse would not happen immediately. It would happen quietly, steadily, as the nutrient supply dwindled and the productive zones contracted, and the fish populations that could not adapt fast enough simply disappeared. The final thing worth understanding about a full AMOC collapse is that it would not present itself as a single, identifiable climate disaster that the world could respond to collectively with a shared sense of crisis. It would arrive as a cascade of compounding stresses, each one manageable in isolation, each one feeding the others until the combined weight exceeds the adaptive capacity of the systems involved. European agricultural output declining at the same time that South Asian monsoon disruption reduces rice and wheat yields. North Atlantic fisheries contracting while coastal flooding from sea level changes, themselves accelerated by the absence of AMOC's slight sea level suppressing effect on European coastlines, displaces communities. Food prices rising globally while political systems already under pressure from inequality and energy costs face the additional demands of climate adaptation. Migration pressure building as regions become agriculturally marginal before formal policy frameworks have acknowledged the scale of the threat. Each link in the chain is, by itself, a manageable problem, or at least a problem that has been managed before. The interaction of all of them simultaneously, in the absence of the stable climate background that AMOC has been providing, is a different category of event. It is not the end of civilization, but it is the end of the specific civilizational conditions under which everything built over the past 10,000 years was constructed. Which brings us, inevitably, to the question that ought to be the loudest one in any conversation about this topic. Why are we only finding this out now? The Utrecht breakthrough did not emerge because new instruments were invented or new data was collected. It emerged because a supercomputer was finally large enough and a research team was finally funded adequately to run a simulation at the resolution required to see what the data was already showing. That is a remarkable and not particularly flattering statement about the state of climate science infrastructure. Ocean modeling has historically been one of the most computationally demanding areas of Earth science, and for decades, the practical constraint was not scientific imagination or theoretical understanding. It was processor time. Models were run at coarser resolutions, Not because finer resolution was unnecessary, but because it was computationally unaffordable. The AMOC research community knew that coarse grid models were missing dynamics important to boundary currents. That was documented. The case for building finer resolution models was made repeatedly in scientific literature. The computational investment required was simply not prioritized at the level needed to deliver the results that the Utrecht team has now published. There is no conspiracy in that. There is no suppression. There is something arguably more troubling: a structural tendency to underfund the most consequential long-range monitoring and modeling programs in Earth science while over-indexing on shorter-term, more immediately policy-relevant work. The 30 years of satellite data that confirmed the Gulf Stream drift existed. The theoretical framework to interpret it did not, because the model resolution required to generate that framework was not funded in time. We did not build the tools until very recently, and the tools told us something we needed to know 30 years ago. At this point in a story like this, a certain kind of viewer will be composing the question: was this information actively suppressed? It is a fair question to sit with, even if the honest answer is more complicated than the version most satisfying to either side of that debate. There is a well-documented history of organized campaigns to introduce doubt into climate science, the fossil fuel industry's funding of think tanks, the strategic amplification of dissenting voices beyond their scientific weight, the internal memos from energy companies acknowledging their own research on climate risk while publicly contesting it. These are not conspiracy theories. They are documented historical facts available in court records and published journalism. What is not documented, at least not to any degree that survives scrutiny, is a specific campaign to suppress AMOC research or to prevent the development of high-resolution ocean models. The explanation that fits the available evidence is less dramatic, but in some ways more disturbing. The AMOC story was delayed not by active suppression, but by a combination of computational limitation, funding prioritization, and a scientific culture that appropriately resists drawing strong conclusions from incomplete models. The suppression, if that word applies at all, was structural rather than deliberate, built into budget cycles, peer review standards, and the institutional caution of scientists who know better than to overclaim. The result, however, is functionally identical: a 30-year gap between the collection of the warning signal and the recognition of what it meant. The most persistent counter-argument to AMOC concern, the one that gets recycled in comment sections and occasionally in more formally presented skeptical takes, is that the Atlantic circulation has always varied naturally, that the current slowdown is within the envelope of historical variability, and that climate scientists are pattern-matching observations to their preferred narrative of catastrophe. It is worth taking this argument seriously enough to actually engage with it, because the data required to rebut it is genuinely interesting. Paleoclimate proxies, isotope ratios preserved in ice cores drilled from the Greenland ice sheet, foraminifera assemblages in deep-sea sediment cores, pollen records from lake beds, allow scientists to reconstruct AMOC-related conditions going back hundreds of thousands of years. What those proxies show is that the current AMOC state is the weakest it has been in at least 16 centuries. That is not within normal natural variability for the Holocene, the geological epoch that encompasses all of recorded human history. The Younger Dryas was caused by a natural process: glacial meltwater. Nobody disputes that natural processes can disrupt AMOC. The argument that the current disruption is therefore natural confuses mechanism with cause. Yes, freshwater dilution of the North Atlantic is a natural mechanism. The source of the freshwater currently responsible: accelerated Greenland melt driven by a global average temperature increase of approximately 1.2 degrees Celsius above pre-industrial baselines, itself driven by greenhouse gas concentrations at their highest level in 3 million years, is not natural in any meaningful sense of that word. The natural cycle argument, examined closely, does not hold. The decision-theoretic case for treating AMOSI collapse risk as an urgent priority does not actually depend on certainty. It depends on asymmetry. Consider the two possible errors available to policymakers confronting this situation. Error 1. We treat the risk as serious, invest substantially in monitoring, emissions reduction, and adaptation planning, and it turns out the collapse does not occur, either because the timeline was longer than estimated or because action was sufficient. The cost of error 1 is significant resources spent on a problem that did not materialize on the feared timeline. Error 2. We treat the risk as uncertain enough to justify continued inaction. Emissions continue. Greenland melt accelerates beyond the linear projection. Stage 1 progresses faster than the conservative estimate, and collapse occurs within the lifetime of people currently alive. The cost of error 2 is not merely expensive. It is the permanent disruption of the climatic conditions that allowed civilization to develop, affecting food systems, water access, and political stability for billions of people, irreversibly and on timescales spanning centuries. These two errors are not symmetrical. The cost of acting and being wrong is measured in economic resources. The cost of not acting and being wrong is measured in civilizational function. Any rational risk framework, any framework at all, assigns a higher priority to avoiding the catastrophic, irreversible outcome than to avoiding the merely expensive one. The asymmetry problem is not a scientific question. It is a question of values and logic, and the answer to it is not ambiguous. There is a concept in the search for extraterrestrial intelligence called the Great Filter. The idea that somewhere in the progression from simple chemistry to spacefaring civilization, there exists a barrier that almost no species successfully passes through. Most discussions of the Great Filter focus on dramatic, sudden events, asteroid impacts, nuclear war, runaway artificial intelligence. But there is another version of the filter that is quieter and arguably more plausible as an explanation for a universe that appears empty of advanced civilizations. The slow filter is not a sudden catastrophe. It is the cumulative effect of a species' inability to respond adequately to threats that develop gradually, that present themselves as ambiguous until they are not, that require coordinated long-term action against a background of short-term competing pressures, and that do their most critical damage precisely in the window between "we should probably pay attention to this" and "we are now out of time." The AMOC story fits this pattern almost perfectly. The signal existed for 30 years before the interpretation existed. The interpretation now exists, but the window for meaningful intervention may be narrowing. The system most responsible for the climatic stability that allowed civilization to develop is displaying the early phase warning signals of a failure sequence, and the primary response to date has been insufficient funding for the models required to understand it. The warning was not hidden. It was recorded, measured, archived, and present in the data the entire time. We built satellites and sent them into orbit. We measured the ocean surface to the centimeter for 3 decades. We stored every number. We just didn't build the interpretive framework quickly enough to understand what we were looking at. We do now. The question that remains, the only question that actually matters from this point forward, is what we decide to do with that knowledge, and how much time we have left to decide.